Hello, my name is McGuire Hodson, and this is my lab report for Lab 5, and the topic that I chose was to model the motion of a falling slinky. The purpose of this lab is to model and understand how a slinky extends, including compressing and stretching, using Tracker and VPython. This lab is based on Newton's second law of motion, which of course states that force is equal to mass times acceleration, and Hooke's law, which states that the spring force is equal to negative Ks. The computational model made in VPython simulates the motion of a slinky and can be compared to the actual motion of a slinky seen in a video. The model demonstrated the predicted motion of the top as linear and the bottom as logarithmic. This is very similar to the observed data. The computational model includes the effect of gravity, Newton's second law, Hooke's law, and the conservation of energy. There are three main types of energy that are observed: gravitational potential energy, spring potential energy, and kinetic energy. The system is the slinky and the hand that controls it, while the surroundings are the environment around it. The assumptions for the model are that the spring obeys Hooke's law, it behaves ideally, and the spring only moves in the y dimension. The model isolates the pure stretching behavior, allowing to focus on the motion of the slinky over time. So this image displays Hooke's law, and this displays Newton's second law, which again is equal to force times, which states that force is equal to mass times acceleration. For the computational model, the initial top position is 0.2 meters, and the initial bottom position is negative 0.2 meters. So therefore, the center of the spring, which would be the origin, which is at, of course, 0 meters. The stretch rate is 0.2 meters per second, and the slinky stretches for 1.5 seconds. The time step is 0.1 seconds. The spring has 20 coils. It has a radius of 0.05 meters, and it has a thickness of 0.01. In the model, a spring system is observed in only the y dimension. The motion of the top and the bottom parts of the spring are observed. In the code, the motion is graphed over the time period of 1.5 seconds. In Tracker, a video gave data of both the top and the bottom parts of a spring. This is also modeled over 1.5 seconds of 0.1 second intervals. And for both the model and the video, the origin is the center of the compressed slinky. So this is the relevant code for the model, and this is the slinky that was shown in the video. So the model predicted the motion of the top part of the slinky as linear and the bottom part as logarithmic after a few instances of being still. This is similar to the data, although the motion in the data was, of course, less consistent. The model predictions and data are likely slightly different because of external forces acting on the system, which include air resistance and sideways vibrations. So this is the height in the positive direction versus the time, and this is the height in the negative direction versus time, and then this is the model prediction. As you can see, is much more perfectly linear, and this is the model prediction for the bottom position. After a few seconds, it is almost perfectly logarithmic, which differs slightly from the data. So, as in the video, the bottom of the model stayed stationary for a few instances. Initially, the initial forces are not strong enough to overcome inertia as well as other resisting forces. If the spring had more significant air resistance during its motion, the motion would be damped. The top would still move upward, but it would slow down over time instead of stretching at a constant rate. The bottom would also begin moving more slowly, and the overall stretch would be less than that predicted by the initial model. If the spring were stiffer, having a higher spring constant, it would resist deformation more strongly. In the model, the top position would rise more slowly because the spring would require a greater force to stretch, and the bottom motion would be more delayed. The model's prediction of motion varies slightly from the observed motion. This is due to a variety of sources of error, including incorrect model assumptions and incorrect initial parameter values. Additionally, outside forces outside of the system could have affected the spring that were not accounted for. So, despite the errors in the experiment, the tracker data showed the top motion as linear and the bottom motion as logarithmic, which was expected. Overall, this lab provided valuable insights into two-dimensional motion, and it demonstrated the effectiveness of using computational models to predict the behavior of physical systems. And that's all.